Let's start off. Can fun everyone. So all those scans on. Let's start off. So last thing we did was the wave speed. Great. Next thing, if you have speed and all that stuff, that means there's also energy also involved in the system. Energy in a progressive wave. There are the rest. So many people are absent today. Now, if you take a string, so this dotted line is your natural length of the string. So when there is no wave, nothing, the string would have been like this. You need to understand in waves on a string, right? The strings are not ideal. They do stretch a bit. So when this thing stretches, now if you look at this point here, there are 2 points which we want to look. If you look at this extreme position ka particle, look at this, what happens. The natural length used to be this much in dx. When it goes up, if you notice, the length is still the same. The slope is 0. So if you take a segment at the extreme position, the elastic potential energy is 0. So remember, in waves, when you say potential energy, it is not gravitation, it is elastic potential energy. And kinetic energy is also 0 because it's at the extreme position. So like I said, these strings are not ideal. They do stretch a little bit. They kind of behave like springs. And extreme velocity speed is 0. So if you take a small segment at an extreme position, it has no energy. Same thing, if you take a small segment at the mean position, so this green one was the natural length, you can clearly see here it becomes this big. Means it stretches a lot. Here at this segment, the potential energy is maximum. Kinetic energy is also maximum. This is the first time you're seeing where both are maximum and both are 0. So the thing is, energy is not conserved in a string. Obviously, if you think about the definition of a wave, what is a wave? In a wave, energy and momentum are transferred. If energy is constant, how will it get transferred? Since the energy is continuously moving. So if you look at the picture, this is what is happening. Initially, when the wave is like this, after some time, this wave pulse becomes like this. So this position, which is extreme, see what happened. So this was which is at the mean, it went up. So it lost energy. This guy who's at the extreme came to the mean. This guy gained energy. So energy is continuously moving forward. Getting it? So the things at the mean positions are reaching extreme position, they're losing energy, and the extreme positions are reaching mean position, they're gaining energy, and so on. So here we are talking about a small segment dx. A segment dx at extreme position has potential energy is 0, kinetic energy is 0, energy is not conserved. If you take a small segment dx at the mean position, Potential energy is maximum. Kinetic energy is also maximum. This will be a good theoretical question. They will say a small segment dx is taken at the extreme position. Which of the following is true? Potential is minimum, kinetic is maximum. Kinetic is maximum, potential is minimum. Both are maximum, both are minimum. Most people will think energy is conserved, so one is maximum, one is minimum, which is wrong. Both are zero here. So here, when you say potential energy, it is the elastic potential energy due to elongation. This is not your gravitation. Then you can just see this, and theoretically, by a picture, you can tell energy is not conserved. But let's prove it mathematically also. So energy of a segment is not conserved. Clear, everyone? Let's try to get a formula for this potential energy. So the potential energy of a segment this is elastic potential energy of a segment. This is given by half sorry, dx dou by dou x whole square dx. How did we get this? So let's say this is your dx, very small piece. So dx has become this much. If you take this as theta, this has become dx by cos theta, like hypotenuse there. So the elongation in the string dE is elongation in dx segment. So in natural length, a string of dx becomes dx by cos theta when it stretches. So we get elongation is dx into sec theta minus 1. Remember what we are doing this for very small amplitudes. When it's a small amplitudes, meaning if wavelength is 1 meter, we're talking about amplitude of 1 or 2 millimeters. Then we know work done by internal conservative forces will be tension into dE. So you can say work done by external forces here. So all this work done by the tension will actually go into this internal energy. So this will be tension and dE will be dx. Sec theta will be 1 plus tan square theta power half minus 1. Since the amplitude is very small, theta will be very small. You can use binomial approximation. This will become 1 plus half tan square theta minus 1. 1 will cancel. You end up with half t dx tan square theta. Tan theta is nothing but dv by dx. Dou y by dou x whole square. We use partial differentiation because there are two variables. So theta will be small. Therefore, tan theta will be small. So 1 plus tan square theta whole power half will be approximately 1 plus half tan square theta. Again, not a really great thing, but yeah, approximations. The kinetic energy is the easiest one. Kinetic energy will be half dmv square. dm will be mu dx. V particle will be dou y by dou t whole square. There, these are the two formulas for kinetic energy and the potential energy. Yeah. Now let me just put it down. There is something more interesting here. So half tension dx dou y by dou x whole square. You can use this for any type of wave. Because if you see, I didn't take only a sine wave. You could have taken any random wave. As long as it's the wave equation, it works. This will be half mu dx dou y by dou t whole square. If you remember, v particle is minus v wave dou y by dou x. So, and v wave is nothing but root over t by mu. So if you actually substitute this in the kinetic energy, half mu dx t by mu dou y by dou x whole square, you end up with half t dx dou y by dou x whole square, which is actually the potential energy. Again, I didn't take any particular equation. We proved. So in a wave, doesn't matter which wave, the kinetic energy and the potential energy of segment are always equal. They always go to maximum and they come to minimum at the same time. So these two functions will be same. They have equal values. So if someone asks you for the total energy, then you just add them up. The total energy is potential energy plus kinetic energy, which you can normally I prefer the kinetic energy formula because it is easy to remember. Na half dmv square. Dm is mu dx and v is dou y by dou t. Instead of that 10 potential energy formula, this is more convenient to use. So 2 times kinetic energy of dx. It doesn't matter. So for any wave, the potential energy and the kinetic energy of a segment is equal. That's why they both go to maximum and both go to zero at the same time. Okay. You can copy down those two formulas if you want. See a question based on this. Let's see. Going ahead, any doubts so far? So we have a triangular pulse like this. This V wave is V. Mu is the linear density. This length is L. This amplitude is A. L is much, much greater than A. So the amplitude is very small. Find the energy of this pulse. Again, remember, this is hypothetical. You can't generate this kind of waves on a string. You can't have sharp points. The velocity becomes undefined there. So how much energy does this wave contain? Obviously, when you're sending waves, you will get tired. So you're actually sending energy through this. So how much energy does this one pulse consist of? Find kinetic energy and potential energy of the pulse. Okay. Get this, you got a minute or two. Any answers? You just need to find kinetic energy. That takes care of everything. So if you take this as theta, so tan theta will be A by L by 2, 2A by L. Tan theta is nothing but dou A by dou X. So V particle will be minus V wave dou A by dou X. V wave is V, dou A by dou X is 2A by L. This is your dou A by dou T. Therefore, kinetic energy of a segment dx will be half mu dx dou y by dou t ka whole square. If you want kinetic energy of the pulse, you have to integrate. Half mu dx. Luckily, this is constant 2ab by L ka whole square from 0 to L. That's the total length of the pulse. This turns out to be 2ab square by L into mu. This is the kinetic energy of the pulse. This will be also the potential energy of the pulse. Total energy will be double of this. 2a square v square mu by L. If you see, the only thing is dx here. That will be simply integral x and limits will go from 0 to L. Any doubts on this? That becomes straightforward. If they give you some kind of a parabolic function or something, then this will be in the form of y is equal to x square or something. So yeah, then it would change a bit. Then your dy by dx will be 2ax or something. Then when you integrate, you'll get in form of x square dx. So you can figure out from there. So we took a simple thing, but they could have given any kind of weird function. It would have worked. Because if you see, when I proved this, I took some random function here. I didn't take anything. Even though that curve looks like sine, I didn't use it anyway. Clear with this? Yeah, so this is again for a non-standard equation. So what happens if I use this for our standard equation? For our sinusoidal wave equation, y is equal to a sine kx minus omega t. The potential energy of the segment, half tension dx dou y by dou x whole square. This will be t dx dou y by dou x will be a into k cos kx minus omega t ka square. And we know v is equal to root over t by mu. So tension will be mu into v square. So this will be half mu v square dx a square k square cos square kx minus omega t. This is the potential energy of a small segment at time t. So if you see, energy is not constant, energy is fluctuating continuously. And we also know v wave is equal to omega by k. So omega is nothing but vk. So this v square and k square will become omega square. So this will be half mu a square omega square dx cos square kx minus omega t. That's your potential energy of a segment dx at time t. Similarly, if I do the same thing with the kinetic energy dx, the formula will be half mu dx dou y by dou t whole square. We have already proved this. If you do this, you will get the same answer as a potential energy. You'll end up with half mu a square omega square and dx cos square. Because when you differentiate with time, omega comes out. Kx minus omega t. You will get the same thing. So if you take the total energy of a segment dx, that will be potential energy dx plus kinetic energy dx. There, this is a mathematical proof that the energy is not constant. Mu a square omega square dx cos square kx minus omega t. You can see the energy fluctuates with double the frequency. This is the potential energy of a segment, total energy of a segment at time t, which is not constant. Yeah. But then again, the problem with this thing, since if you take even a normal wave, which has a frequency of 20, 50 times, this is oscillating 50 times per second. So instantaneous things doesn't really make much of a sense. So we can take average. So if I take power instantaneous, and that will be dE by dt. This becomes mu a square omega square dx by dt cos square kx minus omega t. That becomes mu a square omega square v wave cos square kx minus omega t. So this is the power instantaneously. That means if you take a string and if you're generating a sine wave, you're actually spending this much energy every second. This is your instantaneous power in a dx segment. Or you can say instantaneous power you're sending through the wire. So if you take the average power, we know the cos square ka average value will become half. That will become half. So this average is half. We have seen this in AC also recently. The average value for cos square is this thing. Half mu square a square omega square v wave. There, this is your standard formula for power. This is an average power that gets transmitted through the string. Yeah, since the frequency is 2030, you're doing it 20 times per second, it is so fast. You can average also makes sense. That's a standard mains level formula. Everyone should remember that. Mains may they don't care about all the derivations. Again, what is intensity? We have seen this before. Intensity is simply power by in area at which passes through. So here's the cross-sectional area of the string. Because all this power is going through the string. This becomes half into mu by area a square omega square v wave. Now we know rho is your volume density. Rho is mass by volume, which is mass by area into length L. So rho becomes actually mu by A. So intensity is half rho. So kind of, if you see the power and intensity, they look same, but be careful in that it is mu, which is linear density, and here it is rho, which is volume density. This is the intensity that is passing through the wave. Important, we are going to use the same thing in sound waves later on. Mu is your linear density. Rho is your volume density. And that's the relation between rho and mu. Because mu is mass by length, if you divide by area, it becomes mass by volume, which is rho. There, these average formulas are important at a mains level. Clear with this? Any doubts on this? Others, do keep your cams on. Let's see a question based on this. We have a tuning fork. We have a tuning fork. Frequency is F. This frequency is also F. So when this is vibrating, you are getting a wave. This is attached to block mass M. This is attached to block 2M. This amplitude is A. This amplitude is 2A. This is mu. This is 2 mu. Let me say like this. Let this be radius rho. This is a rho. R is the radius of the wire. This is 2R. Yeah. Find the ratio of power transmitted. In the string 1 and string 2. So you took two ropes of same material rho, but they have different thickness. One is radius R and one is 2R. Means one wire is thin and the other wire is thick. But they're made of same material. Blocks are M and 2M attached, so they will generate the tension, because without tension, the wave will not travel only. So one tuning fork is horizontal, one tuning fork is vertical. Amplitude is A and 2A. Find the ratio of power transmitted in the strings. Again, this is the formula we have to use: half mu A square omega square V wave. Just formula substitution, but yeah, let's see. There's a trap. Let's see whether you'll figure it out. Half mu A square omega square V wave. Let's get this. Anyone not clear with the question, please ask. Right. 256 root 2. कितना difference है answers में? Let's see. We have two answers. One you have root 2 and one is 256. I don't know the answer. Let's see when I need to solve. I just made too many variables. 30 seconds more. One by 8 root 2. 1 by 256 root 8. You could have just simplified it more, Narek. God, who leaves an answer like that? Idiot. 256. We have 256. Let's see. First of all, I hope you guys remember this. If the frequency, when you keep it horizontal, frequency of the wave is f only. Here, frequency of the wave is 2f. That's the main trap actually. You guys remember this? When you keep it horizontal, you'll get double the frequency. And what about mu here? So here mu1 will be rho by area. No, reverse. Rho is equal to mu by area. So mu is equal to rho into area. So mu is proportional to r square. Pi r square, no, cross-sectional area. Great. So now let's see the formula. So the power P1 will be half mu. So if you look at the formula here, we have P is equal to half mu a square omega square v wave. So P1 will be half, mu will be rho into pi into r square. Amplitude is amplitude square. Omega will be 2 pi f whole square. V wave will be root over t by mu. T is mg by again mu will be rho into pi r square by this is P2. This will be rho pi. Sorry. 4r square 2 by whole square 2 pi 2f whole square 2 mg by rho pi 4r square. There. This much is there. Then if I solve, half goes off, rho goes off, pi r square a square, this. So numerator full goes off. So this is gone. This is gone. This is gone. This is gone. So denominator me left with 1 by 2 square. 2 square. There is 1 4 here. Then you have root over 2 by 4. That's 1 by. That's 1 by root 2. Did I miss something else? Looks fine. So that would be 4, 4, 4. 16, 64, 1 by 32 root 2. Jay, I leave it to you that this you can solve. I got 1 by 32 root 2. Could be wrong, but yeah, looks like some people are saying yes. So see what is the answer. So it is just a matter of substituting, see where it went wrong. Clear with this? Like I said, I changed too many variables. So it means they'll change any one or any two maximum. Especially the tuning for keeping horizontal vertical, that most people don't realize it. Yeah, that's a bit about energies and powers and everything. So energy is not conserved when a wave goes on a string. Next thing, principle of superposition. So if you send two waves on a string, what happens? Again, understand, waves are not any physical entities, they're simply disturbances. So when a wave passes on a string, what it is doing, it is simply disturbing all the particles. And when you join the position of the particles, it looks like a bump. So technically, if you ask me, is there a wave? There's no wave. Wave is simply nothing but the combination of disturbances is what you call as a wave. All right. So if you send two waves on a string, what will happen? One wave is trying to push you by 5 centimeters. Another wave is trying to push you by 3 centimeters. So together they'll push you 8 centimeters. So they'll just superpose. If one guy is pushing 3 centimeter and one guy is pushing -1 centimeter, that will be 3 minus 1. So the waves simply add up vectorially. The resultant would be the sum of the individual waves. So if you take case 1, let's say waves are in the same plane of oscillation. So y1 is, let's say, a1 sine kx minus omega t. You can write omega t minus kx also. I told you the difference, right? Omega t minus kx is your sine function. Kx minus omega t will be the inverse sine function. So it really doesn't matter much. So let me write this also for some time. Omega t minus kx plus 5. So how do you add two sine functions? We did this recently in alternating circuit phasors. Y resultant will be y1 plus y2. So we can replace this with r into sine omega t minus kx plus 5. If we send two waves in the same direction, in the same phase of oscillation, they'll simply add up. So this is how we add up. So this is your A1. This is your A2. This will be your resultant, and this will be your alpha, and this will be your phi. You know the story here. So R will be root over A1 square plus A2 square plus 2A1 A2 cos phi. Tan alpha will be A2 sin phi. So you can even add multiple waves, A1 plus A2 cos phi. So there. So if you give me two waves, this is what I do. Clear with this? Case 2. What if they're not in the same plane of oscillation? Waves are oscillating in different planes. Think about it. If you take a string, if I move it up and down, the wave will go up and down. But I can also do left and right now. You're getting it? There's nothing like I should send it only up and down. I can send it left and right also. Again, I'm taking very special cases. You can send the waves opposite to each other. We will see later on that becomes something called stationary waves. You can send different amplitudes, same amplitudes, a lot of things. But basic is this only. They just add up. So example, if I take something like this, so listen carefully here. Y is equal to A1 sine omega t minus kx or kx minus omega t, whatever you want to take. J cap. So exactly what are you saying here? When you say this x here, this is the direction of propagation of the wave. So this thing is going in the direction of x-axis. So here, y here, this is a string, so particles oscillate along y direction. Suppose if I write like this, z is equal to b sine kx minus omega t. So they're basically looking that inside. Now, for example, someone writes like this, x is equal to a sine kz minus omega t. What is the meaning of this? The wave is going along z-axis and the particles are oscillating along x-axis. Is that making sense? Because remember, what is the transverse wave? The particle should oscillate perpendicular to the wave. That perpendicular can be in any plane. So again, this is the wave moves along x-axis. particles oscillate along z direction. So if you try to combine these two guys, luckily, if you see, I did give good functions. Sometimes, right, the functions are not good. Then what you do, you can do nothing. You just say y plus z and done. You can't add them anymore. If they give you position and time, then you can add them and get some value. So if I try to add these two, this is how it would kind of look like. So let's say this is your x-axis. The wave is going in this direction. So this is your y-axis. This is your z oscillation. Making sense? So when you add these two, then how do you get a wave? Now, because both are in the same thing, you can see this wave actually goes at an angle. The resultant becomes like this, where this direction will be aj cap, and where this direction will be bk cap. So you can actually find this angle alpha. So tan alpha will be a by b. So this whole wave will actually oscillate at a different plane, just like you're adding two perpendicular vectors. Okay with this. So waves, right? Like I said, they don't care. Each wave has its own agenda. Like I want to move this particle in x, y direction. The other wave says I want to move in z. Now, if both of them decide to do what they want, then one guy is moving in y and one guy is moving in z. The resultant, superposition. If you remember, this was the whole principle of superposition. If there are two events, event one gives you effect one and event two give effects two, and both are independent of each other, the net will be event one, effect one plus two. Clear with this, everyone? So that this is how you can put it in equations and all. You can add even more types of waves, but let me take something more simpler. Let's say we have a square pulse and we have a triangular pulse. Again, remember, these are hypothetical. You cannot create these things on a string. These are sharp edges. So mostly these are voltage pulses. Did you ever see in movies, the heroine or villain is dying or hero is dying? You know, there is a signal like beep, 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 and then he died. Seen the typical movie story? Then heroine comes and cries, and then again it comes, and then again he survives. Those are actually voltage pulses. So a typical story. So that is how it works. So this is 1 unit. That could be anything. 1 unit. 1 unit per second. 1 unit per second. Yeah, only the shape is different. Everything else is same. So the question would be like this. So this is the picture at t is equal to 0. And I want to know if these two waves combine, how will they look like at t is equal to different times? Let's say at t is equal to 1 second. How do you think they will look like? At t is equal to 1 second, the square will come till here and the triangle will come like here. They're about 2 meters, isn't it? Just for convenience, I'll put a red color. If I say t is equal to 1.25, how do you think it will look? 1.25, if you see, each wave will travel 1/4. So if you travel 1/4 and if I travel 1/4 in the opposite direction, we will have a distance of half between us. Again, the pictures are not up to scale. So this is how the picture will look, isn't it? So if you combine these two, then what do you get? Again, what are you exactly adding here? See. So look at this thing earlier. This is 0. This is 0. This is 0. This is 1/4. This is half. This is 3/4. This is 1. 3/4, half, 1/4, and 0 and 0. So blue color values will be here 1, 1, 1, 1, 1, 1, isn't it? So that means the blue one is trying to push the particles by 1 unit. That's what a square wave does. But the triangle is pushing different values. Now, when I add them, 1 plus 0, I'll get 1. 1 plus 0, 1. 1 plus 0, 1. 1 plus 1 by 4, 1 plus 1 by 2, and so on. So if I actually draw this picture, this is how it looks. So this red color wave will climb the blue wave. Isn't this how it looks? Wherever they overlap, that wave will get pushed by 1 unit upward. That is the meaning of adding a square wave. Is the picture clear, everyone? So this is the superposition. This is the point where they're adding up. So if you add 1 to all these points, what will you get? You will get, this thing will get elevated, isn't it? Is that making sense? If you add 1 unit to everything, the whole thing will rise by 1 unit upward. It's like, if you see the equations now, this is y is equal to x. What is y is equal to 1 plus x? 1 unit up, no? So that the picture for this guy will look like this. A rhinoceros. Kind of. So 1.5, what do you get? 1.5, they will completely overlap. You will get a house. Clear with this? And this whole height becomes 2 units. Is this clear, everyone? Now, I'll give you something like this. Now, you guys try. Clear, na, Poroja? Ignijit, Pratik, Devansh. Great. We have two triangular pulses. This is the scenario t is equal to 0. Draw the shape of the pulse at 1.25, 1.5, and 1.75. Let's see. How does this look like? 1.25. So it will be like 1/4 inside. So 1 second may they will be exactly like this. So in half second, what will happen? This will travel 1/4, that will travel 1/4. So I think if you take the center here, they will cross like this. The centers will cross. Isn't this how the picture looks? So see, this is 0, this is 0, this is 1/4, this is half, this is 3/4, this is 1, and then again 0. Look at the blue guy. This is 1, 3/4, this is half, this is 1/4. Do they meet half and half or 1/4 and 1/4? No, it looks right only. This is 0 and so on. So now when I add this, so this is how it looks. So 1, this will go till 3/4. From 3/4 something happens, see. 3/4. I think I had a mistake. No, it will not be 3/4. The numbers are wrong. So it will be from here it will start. This wave will come to half of it. So 0, 0, this is 1/4, this is half, this is 3/4, this is 1. This is 3/4, this is half, this is 1/4, 0. Make sense? It looks like this. Now see, 0 plus 1, 0. Then this graph will go on till half. Now from here something happens. Half plus 0, half. 1/4, 1/4, half. Half plus 0, half. Can you see? So that region where they overlap, it becomes a constant. It's like adding y is equal to 1 plus x and adding y is equal to 1 minus x. When you add them, you get 2. You get a constant number. Meaning the rate at which the blue is decreasing, at the same rate the red is increasing to compensate. It becomes constant, and then the graph will again go up like this, and then again decreases. You get Batman. Clear. So at 1.25, you get Batman. 1.5 is easy. 1.5, they will come like this completely. You get a square. How does 1.75 look like? That's an interesting one. Try. I'll give another 30, 40 seconds. 1.75. Did you get it? This will look a little weird. they would be like this. So again, if I try to put some values here, you'll get a 0. This guy will be half. This guy will be 1. This guy will be 3/4. This will be 1/4. This guy will be 1, 3/4, half, 1/4, and 0. That means when you add 1 plus 1 by half, you always get 3/2. So this thing increases, then it becomes constant like this, then it decreases like this. Clear with this. It looks something of this sort. You can check out the numbers. Got it? So there, this is how you can add superposition. I still took a triangle and square and all. If they give some weird shapes, it becomes more complex.
A simple introduction to the topic wave, produced by the Hertfordshire Science Centre. This mechanical wave machine will be used to generate both pulses and waves. It's called the Vinicum wave machine, and it belongs to the Royal Institution in London. The machine consists of horizontal bars which are threaded together with wires.
So are you guys able?
And the reflected pulse is upside down. What would happen if two such pulses were sent at the same time but from opposite ends of the machine? Because both pulses are started by moving the hand upwards, we'll call them positive pulses. Let's see that again, but this time freeze the pulses as they meet. The pulses add together and form one larger pulse for a moment. This time, a positive and a negative pulse move towards each other. Did you see how they combined? We can see that again, and this time freeze the motion. This time, when the pulses meet, they briefly cancel each other out. You have just seen how pulses meet, but do they pass through each other or simply bounce back? We can solve this problem by sending a single pulse from one end and two pulses from the other. Watch what happens after they meet. Clearly, the pulses pass through each other and carry on as if they'd never met. Here it is again.
Clear that? Yeah, something happened, right? Clear, right? Able to hear me? Yeah, this Zoom now. Okay. There. Did you see what they did when the two pulses were coming? When they added up, you saw you got a bigger pulse. And when you're sending in the reverse, they cancelled out. And the confusion there was, see, there is a possibility the waves are just bouncing off like as if like particles. So that was the second thing. They said, okay, if you send two small and one big, if they're bouncing off, what should have happened? I should have got two small pulses to the right now, but they pass through. So like I said, waves are not like any material particles or anything. They don't behave like particles. They don't collide and stuff. Because wave is what? Simply a disturbance. They're just moving through. Clear with this? Yeah. Take a break. Come back by 9:44. We'll continue from here. Any doubt so far? Shall come back by 9:44. Next thing. The reflection of a wave. Case 1, fixed end. Let's say we have a wave pulse. And we have a wall. So this point here is that this point is fixed. It cannot move. This is your Y incident pulse. So Y incident will be a sine omega t minus kx. Now, after hitting this thing, it kind of behaves like, perfectly elastic collision. The wave gets inverted. So you get a reflected pulse. Y reflected. Which will be minus a sine. Since it's elastic, there'll be no loss of amplitude. This becomes omega t plus kx. The right traveling wave became a left traveling wave. But remember, normally we don't say minus negative amplitude, so we'll send the sign inside, minus sign. This will become omega t plus kx plus pi. There. So whenever you hit a fixed end, the incident wave and the reflected wave are out of phase by pi. The wave gets inverted. Quite a useful thing. We will going to use this again in wave optics also. Clear with this? Next thing, what happens if we hit a free end? Free end or a massless ring. Now what happens when this pulsar comes hits this ring, because it does not offer any resistance, the ring will go up. When the ring comes down again, it sends a wave in the same direction. So y incident will be a sine omega t minus kx. Y reflected will be a sine omega t plus kx. The right traveling becomes left traveling wave. So here the incident wave and the reflected wave are in phase. Clear with this? So generally this is what happens whenever you have a fixed end or a free end. Other scams on? Now let's see a question based on this. Again, hypothetical thing, the square pulse. There. This is the scenario t is equal to 0. Now see for superposition, how many waves you need? You need two waves. So here, now tell me one thing, when this wave goes and hits a fixed end or a free end, do you think the whole wave will suddenly turn? Whatever is hitting, only that part will keep on getting turned, right? So whenever this is hitting the fixed end or a free end, the reflected wave and the wave which is coming, both will overlap. So draw the shape of the wave at 1.25, 1.5, and 1.75. So here it is a superposition between the wave and its reflected wave. There, now we're combining reflection with the superposition. Let's see. Let me show the first one. So at 1.25, what will happen? 1/4 of the wave gets inverted, remaining 3/4 is still up. So it looks like this. For convenience, I'll draw it in a green color. There, it looks like this, isn't it? So whichever hit, only that part will get inverted. Everything will not get inverted. So when you do this superposition, you will get something of this sort. So they will cancel out. So this will be half and this will be 1/4. At t is equal to 1.5, half of the wave will be ahead and half of the wave will get inverted. The wave will be flat. Making sense? So you just have to treat the inverted wave as a second wave. 1.75, 1/4 is ahead, 3/4 is inverted. The resultant will be like this. Making sense? Now, can you do the same thing for the ring one? Get this, I'll give you a minute. So in case of a ring one, you won't get inverted, you get it in the same phase. So try, you got a minute. Let's see. 1.25. So you have 1/4 like this. This whole thing will look like this, isn't it? This thing just goes up. You'll get double the amplitude. I think 1.75 also looks the same as 1.25. Reflected will be 3/4. Clear with this? There. So that is what happens when you have a reflected and an inverted wave. Clear with this? Great. So now every time you won't be so lucky to get a fixed wall or a free end, what if you have a composite string? Case one, let's say you have taken a light string mu1 and mu2. So mu2 is greater than mu1. So you have tied a thin string to a thick string. So if you look at this point here, now see, if you put mu2 tends to infinity, doesn't it become a fixed end? And mu2 tends to 0 becomes a free end. So this intersection here, x is equal to 0, since it is not a fixed end, but you're tied to a heavy one, so you'll have an inverted wave and you'll have a transmitted wave. So here you'll have y incident will be a incident sine omega t minus kx. So after hitting this, it kind of feels like a fixed part, but not completely fixed. So you'll get an inverted wave. And you also get a transmitted wave. So whenever you have a composite string, the wave will always split into two parts. You get a transmitted and a reflected. This is your y transmitted, which will be a transmitted sine. Remember, the frequency doesn't change, omega t, but the wavelength will change. So k dash x. And it will be minus because it is still traveling in the same direction. This will be y reflected, which will be minus ar sine. Frequency will remain same. It is going in the opposite direction plus kx because it is the same string. So when you go from light to heavy, you get an inverted reflected wave and the transmitted wave will be in phase. Case two, Let's say you're going from heavy to light. This is kind of like hitting a massless string. If this is y incident, we get A incident sine omega t minus kx. In this case, the y reflected will be in phase. So it's like a partially free end, but it is not a completely free end. So you'll get a transmitted wave. Y transmitted will be A transmitted sine omega t minus k dash x. So remember, k dash will change. Because in both the cases, the frequency is same, right? But the wave speed is different, so wavelength will be different. So if you remember, V wave is omega by k. So V wave is proportional to 1 by k. And V wave is nothing but root over t by mu. So I can add that also. Root over t by mu is equal to omega by k. So k is proportional to root mu. So if mu changes, k changes. Now we want to find that A transmitted and A reflected and k dash. So if you can find all these three, my job's done. This itself will be an advanced paragraph question. So what we're doing now as a derivation will be a general solution, will be actually a question. So let's take a very general solution. So we have two strings. X is equal to 0. This is mu1, this is mu2. So mu and mu2 are random values, so they can be greater, smaller, anything. Let's say this is your y incident, which is A incident sine omega t minus kx. So after hitting this, let's say the transmitted, the reflected are in phase. The signs will take care of it. So let's assume they're in phase. Depending on mu1, mu2 values, the signs will come automatically. A transmitted, this will be sine omega t minus k dash x. Y reflected is A reflected sine omega t plus kx. Great. So my job is to find, I know A incident, I need to find A transmitted, A reflected. Now let's consider 2 points, A and B, very close to the origin. They're almost touching each other, but they're on two different strings. A and B are points on the string one and string two. Very close to x is equal to 0. They're literally touching there. Now, be careful here. This is something you have to understand. Forget about the right wave. If you just look at the left-hand side of the wave, on the left wave, how many waves are there? Again, like I said, when the wave comes and hits that point x is equal to 0, will it immediately turn? Will the whole wave just turn? So a part of the wave will turn that will superpose with the incoming wave, isn't it? So on the left hand of the string, the displacement of YA will be because of Y incident plus Y reflected. The most common misconception is this. People think like this. Sir, this Y incident becomes Y reflected plus Y transmitted. That is not right. When you say superposition, what are you doing exactly? It is a superposition of two waves on a string, isn't it? So when you do superposition on the left string, shouldn't take only the YI and YR? There are only two waves on the left string. Is that making sense? The displacement of this particle is because of yi and yr. So the misconception is this: it is not like, yi will come, it will vanish, and then yr and yt will come out of nowhere. As yi is going into x is equal to 0, at the same time yr and yt are being generated. So all three are present at any point of time. Clear with this? Now at point A, how many waves are there? One incoming wave, one reflected wave. If you ask point A, what about y transmitted? A will say, I don't know who is y transmitted, isn't it? Because transmitted is forming on the right string. A does not know who is transmitted. Is that making sense? So basically, there are two waves, incident and reflected wave, superposed on the left string. Superposition, everyone, don't treat it like a mass, 2 kg came and became half kg and 1.5 kg. ऐसा नहीं है. Reflected waves superpose on the left string. Similarly, if you look at the displacement of B, it is only due to the y transmitted. Now, since A and B are very close to x is equal to 0, they're touching each other, they should have same displacement. If YA is not equal to YB, what will happen? Think about it. Let's say YA is 5 centimeters. YB is 3 centimeters. That means there is a hole in the string, na? The wave is discontinuous. But can wave be discontinuous? No. Therefore, YA must be equal to YB. Is that making sense, everyone? So YA is equal to YB, right? Since the wave is continuous. If YA is not equal to YB, you will get a hole. And the string would look like this. We get a discontinuity. So we get y incident plus y reflected will be y transmitted. This is what most people get confused. They feel like, sir, but incident is giving reflected and transmitted. So incident must be reflected plus transmitted. You're getting it? So the problem is you're treating it like some mass. 2 kg mass broke into 2 pieces of half kg and 1.5 kg. You don't do that. This is not a mass. It's not a particle. Clear with this? And it is not like, instant wave will come, it will vanish, and then suddenly 2 waves will come out of nowhere. All 3 waves are there at any point of time. So at x is equal to 0, if you equate all this, so y incident will be A incident sine omega t minus kx, so omega t, plus A reflected omega t plus this thing sine omega t. Y transmitted will be A t sine omega t. So at any instant, we'll get AI plus AR is equal to AT. Clear with this? This is your first equation. Second thing, since we are taking no power dissipation, power incident is equal to, so energy you can say that way. Energy is a scalar quantity, right? Whatever energy is coming, that must be equal to power reflected plus power transmitted. So whatever energy you're sending to x is equal to 0, that should split. What is power ka formula? Half mu 1 A incident square omega square V1 half mu 2 A reflected square omega square V1. This is also mu 1. Transmitted will be half mu 2 A transmitted square omega square V2. And we also know V is equal to root over T by mu. So this formula becomes root over mu1 A incident square root over mu1 A reflected square root over mu2 A transmitted square. Or you can also write this in terms of V only. A incident square by V1 A reflected square by V1 plus A transmitted square by V2, whichever you like. Mu is given, use that. V is given, use this. So there we have two equations, two unknowns. I have all the data. So one from continuity of the function and one from the power, energy conservation. Yeah. Now let's substitute there. A incident square by V1, A reflected square by V1, A transmitted is AI plus AR, whole square by V2. This is A incident square, A reflected square by V1 is equal to A incident plus A reflected whole square by V2. This will become AI minus AR by V1. So AI plus AR will cancel by V2. So from here we get A reflected will be A incident. That will be V2. So A reflected V2 minus V1 by V2 plus V1. There. It's a good formula to remember. V2 minus V1 by V2 plus V1 A incident. If you take that and substitute there, you'll get A transmitted. You have to put it there. So this is plus A plus AI. That will be V2 2V2 by V2 plus V1 into AI. So we define something called coefficient of reflection. So this tells you how much part of the wave got reflected. Like I said, this itself will be a main advanced paragraph question. What I'm showing you as a results. This will be A reflected by A incident. They can ask you coefficient of reflection. V2 minus V1 by V2 plus V1. Remember, V2 is the speed of the transmitted wave and V1 is the incident. So from whichever side the wave comes, that is your incident thing. So if the wave is coming from right side, then mu2 ka thing is V1 and mu1 ka is V2. So it is better you remember as incident and transmitted wave. We don't know because the wave is coming from which way. Similarly, we have something called coefficient of transmission. Which is A transmitted by A incident, which is 2V2 by V2 plus V1. And in both the cases, the wave speed will be same. So V1 by K1 will be V2 by K2. There, this will give you the K ka value also. So V1 by K is equal to V2 by K dash. So K dash will be K into V2 by V1. Like I said, there are three different things that you have. You need to find AT, you need to find AR, you need to find K dash. We got all three. Now, depending on the values, you can get plus and minus signs will take care of themselves. We'll see a few questions on this. There, have a look at this. You can note down the two things in the red box. Those formulas are important. So if you know these results, it looks pretty straightforward. If you don't know the result, then the whole question looks like a monster you have to derive. Let's see a question. Any doubts so far what we did? This was making sense, right? Superposition and energy. In case you forgot also, you can derive it fast. Let's say 4 mu, mu. The y instant will be a sine omega t minus kx. Simple. Find the equation of the reflected and the transmitted wave. This is 9 mu, this is 4 mu. Find the equation of reflected and the transmitted wave. There, like I said, you need to find total 3 things. AR, AI, and K. Let's get this. Yeah, tension will remain same. Na? If the tension is not same, this interface will move. Both are tied to a point, right? It is a massless point, so tension must be same on both the sides. So there must be some block or something tied on one end, which I'm not showing. If the tension is not same, this whole rope will be in motion. Then tension will vary every point. Then it gets messed up. Let's get this. Finish off. It's an easy stuff. Now it is an easier stuff since you know the formulas. Could I show you one? So after hitting this, again, now don't worry about how does this look like, meaning in reflected wave and all, the equations will take care of it. So let's find the speeds first. So V1, we know V is equal to root over T by mu, proportional to 1 by mu. So the main thing is I don't want the speeds also. What I want is just the ratio. So V1 by V2 will be root over 4 mu by mu. So that is 2:1. Great. So what is A reflected? V2 minus V1 by V2 plus V1. A incident is A. So that's 1 minus 2 by 1 plus 2 minus A by 3. That means your reflected equation will be minus a by 3 sine omega t. It is going to the left side, so omega t plus kx. Clear? You know how will the picture look like? Matlab, roughly, so you'll have an idea. This is how the picture would look like. You know, it is going back. You know, it will be inverted. The sign will take care. You don't worry about it. Based on the values of mu and all, the values will take care. Similarly, what is A transmitted? 2v2 by v1 plus v2 into A. So I will take v1 as 2v and v2 as v. So that will be 2v, 2 to 4, 4a by 3. What is the 2a by 3? This will be 2 into v by 3, 2a by 3. This will be 2a by 3 sine omega t minus k dash x. So we know omega is v by k. So v1 by k1 is v2 by k2. So your k dash will be k into v2 by v1, that is k by 2. Clear, everyone? Then, like I said, once you know this formulas, it looks pretty easy, you know. You have to derive. Can you do this guy? 9 mu and 4 mu. Now we know the inverted reflected won't be inverted. Let's see. So here again, same story. So v1 by v2 will be root over 1 by mu, na? 4 mu by 9 mu. 2 is to 3. So for simplicity, let's call it 2v and 3v. And have a rough idea how will the wave look like. So you know it looks like this. So A reflected will be v2 minus v1, that is 3 minus this. I think you'll get A by 5. A transmitted will be 2v2, 2, 3, 6, 6 A by 5. What about K? K dash will be K into omega. V is omega by K. I think I'm writing wrong, I guess. I wrote in this thing wrong. V wave is omega by K. So omega is V1 K1 is equal to V2 K2. That was a mistake. Hmm. So this guy will be v1 by v2 is 2k. This k dash. So that is 2k, everyone. I did a mistake. So v1 k1 is equal to v2 k dash. 2 by 3k. So you're done. So y reflected will be a by 5 sine omega t plus kx. Y transmitted is 6a by 5. There's no minus sign. So like I said, the signs will take care. Omega t minus k dash x. Clear with this? Any doubts on superposition at all? Clear with this? So there. So today, if you see, we saw energy, then we saw superposition, then we saw reflection, then we saw reflection and superposition, then we saw composite waves. So all this is actually, when you see now, this is kind of little neglected part. Whenever normally people do this thing, this is one of some neglected part. This will be the basis for the next part, which we're going to do, which is stationary waves. So in entire waves, one of the important concept is stationary waves. Then it used to be Doppler effect, but Doppler effect they removed from the portion. But still, we are going to do a little basics because bits ke liye to hai. So stationary waves is the most important thing now. Okay. So next class when we catch up, we'll continue from there. We will do that's a new subtopic, so we'll start it fresh. So yeah, with that we'll wrap up for that day. So do make sure to go through this. Chapter is not tough, but you saw, right, lot of results, lot of theory, there's a lot of things. So make sure to go